Okay, YouTube, in this video we're going to be confronting all of the different parent functions, okay? And as a matter of fact, don't say all of them, but 8 very specific ones, including the greatest integer function as well as piecewise functions here. But basically what I want to build into is how we can use the parent functions to quickly graph sketches of transformations of those, as long as we know the basic characteristics of the parent function. So we're actually going to start with what we call the greatest integer function, or anybody in the greatest integer function family. And what I want to do is I want to start by indicating how it is that we denote this. So just like we would write a line like f of x equals x, or a quadratic f of x equals x squared, and so on and so forth, we write the greatest integer function thusly. And we write this little double bar around our input or independent variable here, x. And we would read this as the double bar x as the greatest integer less than or equal to x. So for instance, if I were to say what is the greatest integer that happens to be less than or equal to 1.9, consider the fact that integers, recall, are these whole number values on the number line. So I have like 0, 1, 2, integers can be negative as well. But basically this would go on forever and ever. 1.9 would lie just about right there on the number line. I say, well, okay, if that's 1.9, what is the greatest integer that happens to be less than 1.9 or equal to 1.9? I notice here that on the number line, well, the greatest one I can think of that's less than that is just 1. So we would say that this would be equal to 1. And we'll just kind of look at these examples here. But for instance, let's say, I have the greatest integer less than or equal to negative 1.5. Well, negative 1.5 is right here on our number line. The greatest integer that's less than or equal to negative 1.5 would be negative 2. And let's talk about 3. 3, of course, would lie to the right of 2. The thing here is this: the greatest integer that's less than 3 is 2, but the greatest integer that's less than or equal to 3 is just itself. So this would be 3 here. Okay. So where I've written f of x equals 2 times the greatest integer less than or equal to x, maybe we plug in an f value here. I say, let's go find f of 3 halves. And so I'd say, okay, well then what would this be? It'd be 2 times the greatest integer less than or equal to 3 halves. And we got to think here, 3 halves is 1.5. 1.5 is about right here on the number line. And we say, well, 1 would be less than or equal to that. Basically, what we have to do is evaluate this first. And so we'd end up with this expression now that when we evaluate it, we get 2 times 1, which was the greatest integer less than or equal to 3 halves. In other words, we get 2. Okay. So what I would like to do is really comment on the nature of its graph. You'll notice that we also refer to these greatest integer functions as step functions. And the reason why is because when you graph these, think about this. If you were to plug in all numbers into this function here, into x, that are between 0 up to but not including 1, like a half would go back to 0, 0.75 would go back to 0, 0.99 would go back to 0. Basically, every single y value that you get out of this between 0 up to but not including 1 is going to be collapsed to 0. But the moment you get to 1, think about this. What would f of 1 be if we have double bar 1? It would be 1. So the moment I get to x equals 1, now I'm at a height of 1 on my function, okay? And 1.1 would go to a height of 1, and 1.5 would go to a height of 1. Everything up to 1.99999 would collapse back down to a height of 1, but the moment we get to 2, we'd be at a height of 2. Okay, so you'll notice that this right here, the one thing I want to point out is it kind of starts at the origin, if you ask me, and it kind of proceeds in this up 1 over 1 fashion for good, but you'll notice that we have this open dot on the right side here, because every time we get to the next highest integer, it'll kick up to that height. So at 2, it'll go to the height of 2. At 3, it'll go to a height of 3. But we get this step function here. So while we're going through this video, what I really like to do is fill out this chart here. We'll start down at the greatest integer function, but basically a sketch of its graph, we could say if this is 1, and this is 2, and this is 3, and we'll go negative 1. I'll label it up here, negative 1. And negative 2. Essentially, we would say the graph of this function would look like this. It starts at 0, goes to the right, and doesn't include 1. So I've got an open dot. And then at a height of 1, it goes to a height of 1, and it goes to the right, and it doesn't include 2, because at 2, we're going to be at a height of 2 now. And then we say so on and so forth. It just keeps doing this indefinitely. And we can just kind of use this pattern to kind of piece together the rest of this. We would say, okay, well, here's the left side of my graph. There are my steps. Okay, so that's the basics of the greatest integer function. In terms of how we write it, we write f of x equals double bar of x, and we say domain and range. Now I notice here domain values, you might say, well, there are open dots on here, so there are x values we don't use. But just because this 1 here has an open dot doesn't mean we didn't include it right here. We have a solid dot above 1 here. So the domain, we say domain is actually negative infinity to infinity, and we say the range of this. Now the range, we would say, I would list it this way. We say all y values such that y is an integer. And that's just true for the parent function. Once we transform it, it doesn't follow that rule anymore. So in terms of intercepts, I suppose it hits the x-axis multiple times here. At 0, 0 is a notable one, so I'm just going to write notable. Notably at 0, 0, even though there are infinitely many intercepts from 0 up to but not including 1 there. And in terms of y-intercepts, we could say that's our x-intercept here. Y-intercept is the same. Y-intercept is at 0, 0. And then last but not least, we say, is it even or is it odd? Okay, this function we would say would be, in this case, neither. It's neither even nor odd. Okay, so we're going to run through a nice battery of all of our parent functions now, but essentially I'm going to start up here with the constant function. So a constant function is any function of the form f of x equals c, and I'm actually going to write specifically f of x equals 1. So this constant function, whenever we get y equals a constant number, we're always, no matter what your table of values is, if I were to fill out a table of x and f of x here, basically what I'm going to say, no matter what your x is, okay, you're going to get 1 for outputs. And so it's always going to be at this height of 1 here, and our constant function looks like this. So here's our f of x equals 1, where that's the height of 1. In terms of domain and range, domain, it goes left and right forever and ever, so from negative infinity to infinity it's defined. And then range, the range is just the set of the output 1. It only goes over the output 1. In terms of intercepts, x-intercept, okay, x-intercept, it has none. And then in terms of y-intercept, we notice that it hits the y-axis at 0, 1. Okay? And in terms of even or odd, well, I notice that this has y-axis symmetry. So this is definitely an even function. Okay? As far as the identity function is concerned, we say that this is any function of the form, its parent function at least, f of x equals x, or y equals x. So in other words, if you were to make a t-chart of values here, we say x and f of x, not y, we say f of x here. Essentially, whatever your x value is here, your y value is going to be the same thing. We get -2, -1, 0, 1, and 2. So this is just a line with the slope of 1, and it starts at the origin, goes up 1, right 1, up 1, right 1, up 1, right 1. But basically, this is our identity function right here. So in terms of what things I want to memorize, I know that it goes through the origin here. So in terms of x-intercept and y-intercept, we'll say x-intercept is at 0, 0, and I'm going to say y-intercept is the same. Okay, this is an odd function. And in terms of domain and range, it's all real numbers for our domain, left to right forever and ever, that's our domain. And our range values here are going to be negative infinity to infinity because it always starts down and goes up forever and ever, crosses every output value on the y-axis. Okay, so next up is our absolute value function. Recall that an absolute value function we listed thusly. An absolute value, whatever you stick in here, basically it's going to pop it back out positive again, because remember, absolute value is saying how far away from 0 are you, and distance is never negative. So in this t-chart situation here, we have x and f of x. We'll put in the same x values here all the way up to 2. We can put in whatever we want, but notice that your outputs are going to be only non-negative outputs of this. So our absolute value graph, just like our linear function, kind of starts at the origin. This one starts at the origin and goes up 1, right 1, and then we had 2, 2 on our graph. But when we went left, we said -1, 1, and -2, +2. So our absolute value graph looks like a V. That's its basic characteristic there. Now, domain and range, this one is not going to be as simple as we saw in the last couple here, but we say the domain is certainly all real numbers, so negative infinity to positive infinity, but in terms of range, I notice that it's only values, including 0, up forever and ever on our output axis here. So we say from 0 up to infinity, not including infinity. And in terms of x, I'm going to say and y-intercept on this one. We'll make it a little bit briefer. We say it hits at the origin. That's a notable point that we want to know about. In terms of, is this even or odd? Well, I can say, well, this is definitely an even function because it has y-axis symmetry. Remember, graphically, even functions have y-axis symmetry. All right, our square root function, f of x equals root x. All right, this function's a little bit different in terms of making a t-chart, for instance, here. If we were to do this, we say f of x. I do actually want to put in some negative values here. Recall what happens when you try to take the even root of a negative value here, okay? So actually, you know what I'm going to do? I'm not going to put in 2, I'm going to put in 4, and maybe I'll put in 9 here. But essentially, you know, if we took the square root of -2, we get -2i. In other words, it's non-real. Not real. I'm just going to write that over here for -2 and -1. So its domain is restricted. As a matter of fact, we might as well write the domain right now. We're going to say the domain is a set of all values including 0 and upward towards infinity. We can't plug in negative values into this thing right here. But when we plug in 0, we get the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, the square root of 9 is 3. Essentially what we get is something that, just like the other two graphs we just did, starts at the origin but goes through 1, 1. Okay, I want to point that out. This goes through 1, 1. The last graph went through 1, 1. This parent function goes through 1, 1. Our constant function goes through 1, 1. All of our parent functions have a tendency to do that, okay? But as we go out further here, we say 2, 3, 4. I am going to graph 4, 2, and not 9, 3. But what we get is, you might write yourself a note here, half of a sideways parabola. So half sideways parabola. The reason why is because this is the inverse of our squaring function, which is itself a parabola. But we say half of this sideways parabola. So we can see here that our range, if it's going to keep going up forever and ever, we could say that the range of values that it crosses on the output axis would be from 0 up to infinity as well. And in terms of x and y intercept, okay, again, x and y intercept, we have at 0, 0 at the origin. And is this even or is it odd or is it neither? This is going to be a neither type of function. Okay. So now let's look at our last 4 graphs here, 3 of which we haven't confronted yet. Our quadratic function, another word for this is a squaring function. Squaring, this is very, very popular function. We use this a lot for modeling gravity and acceleration, but we say f of x equals x squared. Our t-chart in this instance, not that we have to make one, but if we were to plug in a nice set of domain values here. They all work, as a matter of fact, and if you square all these, recall this is kind of like absolute value in that when you square a value, it has to come out to be a positive output, except for instead of x and y being exactly equal, since we're taking x times itself, our y values as we deviate away from 0 tend to get bigger and bigger and bigger. So when we graph this, we have 0, 0, we have 1, 1, but we also have -1, 1. And then we say 2, and this is going to be at a height of 4. And as we were to go to the right or to the left, we can see we have some symmetry here. It's just going to keep growing faster and faster. So we get this right here. This is referred to as a parabola. Okay, parabola. So our quadratic function is shaped like a U. We need to know the basic shape. But essentially, we have domain and range. It looks like our domain. Recall, we can square any x value and get a y value back. So as far as the domain is concerned, I can see on my graph here, it goes left to right forever and ever, from -infinity to infinity. But the range, I'm looking at this and I say, well, the range is actually kind of restricted as being 0 and above. So we include 0 and we proceed up to positive infinity. Intercepts, we say x and y intercepts. Also hits at the origin, okay, notable point. And I also want to point this out, and it goes through 1, 1. Every graph we've done that's a parent function has gone through 1, 1 and has at least been centered around the origin, if not going through the origin like our constant function here. But essentially we say, its intercept is at 0, 0, goes through 1, 1. Is it even or odd or neither? We have y-axis symmetry, so this is an even function, okay? So now our last two, our cubic function. It's kind of like our squaring function in that we're going to take an x value, but we're going to cube it this time. And when you make a t-chart of values here, recall that when you square a value, it must come out to be positive. But when you cube a value, it doesn't have to come out to be positive. As a matter of fact, if you cube a negative value, it comes out to be negative. So in this case, -2 cubed is -8, -1 cubed is -1, 0 cubed is 0, and you notice we're going to get some level of symmetry here. It's just that negatives, when you cube them, come out to be negative. As a matter of fact, we can see that this is an odd function because if the point x, y is on the graph, then it implies the point -x, -y is on the graph. We can see that here. -2, -8, +2, +8. So let's go ahead and graph these values here. Notice that it starts at the origin. It goes through 1, 1. As a matter of fact, it goes through 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. We'll squeeze this on here. And it gets really big kind of a little bit more quickly, okay? So we say -1, -1. 3, 4, 5, 6, 7, 8, and here. And so our cubic function, okay, looks like this. And we can see that we have origin symmetry on this one, origin symmetry. So that's what's going to give it away that this has an odd characteristic about it, okay? It's odd. We talk about domain and range. I notice it goes left and right forever and ever. Every input will give us an output, as well as it's going to cover every range value on the y-axis. It goes from negative infinity to positive infinity on that interval of y values here. In terms of x and y intercept, man, I hate to beat a dead horse, but x and y intercept, in this case, we say it goes through the origin on both axes there, and it passes through 1, 1. Okay, all parent functions do this, even this one down here. So our last function is our reciprocal function. We can tune out of this video, but we say, okay, f of x equals 1 over x. When we make a table of values on this one, the interesting thing about it is as our x values get bigger and bigger, I hope you can kind of realize this here, but our y values are actually going to decrease. So let's go ahead and plug in a few. If I were to plug in 0, this is a very important one to talk about. It's undefined. As a matter of fact, I'm going to draw in specifically what we call a vertical asymptote when x equals 0 here, okay? Because it is not defined at that point. But if we were to draw in, say, x equals negative 2, negative 1, 1, and 2, plugging those in, plugging in 1, we get 1 over 1 is 1. 1 over 2 is a half. If we were to plug in, say, 10, we get 1 over 10. It's going to be getting smaller and smaller. And if we go over here, plug in negative 1, we get positive 1 over negative 1, which is negative 1. And positive 1 over negative 2, which is negative a half. So just like on our cubic function here that was odd, we're saying that we have a graph that has origin symmetry here. We notice if 1, 1's on here, negative 1, negative 1's on here. 2, a half, well, negative 2, negative a half. So we're going to graph these out. Let's go ahead and do that. I'm going to exaggerate a little bit here on our graph. Here's 1, here's negative 1. But essentially we get 1, comma 1. Notice it goes through 1, 1. And just because it didn't start at the origin, go through the origin, it kind of is centered there. And we say 2, comma half. 3 would be comma a third. Basically, it's going to keep getting smaller and smaller. One question to ask is, if we go far enough to the right, will 1 divided by a big number ever reach 0? And the fact is, it never does. So we also have a horizontal asymptote at y equals 0. We'd say we get this graph here that is a hyperbola, and it has branches, okay? Negative 1's at negative 1, negative 2's at negative a half. Here is our hyperbola. This is all one graph. So when we talk about the domain of this one's actually an interesting domain. We say, well, it starts way out here at negative infinity and goes up to 0, but it never crosses an x value of 0. So the way we'll write this is negative infinity up to 0 in union with 0 out to infinity, okay? And in terms of range, we say, okay, range starts way down here and comes up to a height of 0, but never gets to a height of 0. So we say negative infinity to 0, and it's also in union with 0 to infinity because it starts at a height of 0 and proceeds up forever and ever. In terms of intercepts, it has none. It'll never hit these. So it is worth your time to memorize the basic shapes of all of these functions here, because what we're going to do in the next video is we're going to start transforming the parent functions to more quickly sketch graphs of these functions that all centered at the origin and all went through 1, 1 and all had their basic characteristics that we memorize. Cheers.